This video covers Chapter 5 of the book. It concerns heat transfer and related field problems. I'll start off by showing the sort of field problems that are covered by the theories in this particular chapter. And then we'll lead on to the quasi-harmonic steady-state equations, which cover these different types of field problems. From this, I'll move on to heat transfer in order to show a particular application of these particular equations and how we can convert these differential equations into equivalent or approximately equivalent finite element equations for analysis. Again, I'll be using heat transfer as the main method to show the application of these equations. And finally, I'll try and give an example to show you how the finite element equations are used in a very, very simple practical problem. So it's split into three parts. First of all, these governing equations for the different field problems, and particularly the governing equations for the heat transfer problem. Then I'll move on to the development of the equivalent finite element equations for heat transfer, and then finally an example showing application of these equations in a very simple finite element example. This table lists the types of analyses that are considered in field analysis. They're listed here on the left-hand side. We have heat transfer, seepage flow, which is slow flow of a liquid through a porous media, electric potential, electrostatics, magnetostatics, and so on. All of these types of analyses are covered by this quasi-harmonic equation that I'll be showing in a minute. And special cases of this are the Laplace-Poisson's equations, Fourier equations, which I will also be introducing for heat analysis. In the mechanical problems up to now, we've only been considering the material property, typically Young's modulus. In these problems, we have a different material property to be considered. So, for example, in heat transfer, we have thermal conductivity. In seepage flow, we have permeability. Electric potential is electrical conductivity, and so on. There are two types of boundary conditions for these problems. We have what's called essential boundary conditions and also non-essential boundary conditions. The essential boundary conditions are necessary for a solution. So at some points around the boundary of the model of the finite element problem, for example, we will need to define in heat transfer temperature, in seepage flow some kind of pressure, and so on. I've listed the other ones here. Non-essential boundary conditions are, for example, heat flux in heat transfer analysis. This is where heat is taken out of the system by an imposed heat flow quantity, heat flux. In seepage flow, it's fluid flow flux, and so on. These, for example, in heat transfer, we might have convection at the surface, and this is a form of heat flux that depends upon the environment temperature and the temperature at the boundary of the part being analyzed. There are also possible sources. For example, in heat transfer, we might have heat generated somewhere within the body of the part. So this would be a heat source. In seepage flow, we might generate internal flow due to some particular source. I will be going through these again, but these would be sources within the body of the material. These are essential boundary conditions at some point on the boundary, And these are non-essential boundary conditions that can also be imposed. They don't have to be there, but they can also be imposed at some points on the boundary. This is the equation for flow continuity. If we consider a cube, dimensions dx, dy, dz, we have inflows, which I've denoted qx, qy, and qz, and we have outflows, which are also given as shown here. They include some gradient of the flow over the distance. The point here is that these inflows should balance the outflows. So for example, Qx could be typically the rate of inflow of heat per unit area. It could be the rate of inflow of a liquid per unit area, or it could simply be the mass of inflow per unit area. So it can represent many different quantities, but in general terms, let's just say the inflow is Qx multiplied by dy dz, where this is the area, and so on. We have for the other terms Qy and Qz as shown here. That has to balance the outflows, which is given by these expressions summated here. If you cancel out terms, remove the areas, all these will cancel out. You end up with this expression here. And this is the equation for continuity or conservation. It's basically saying if there is a change in this value due to something taking place, then it has to be balanced by changes in these other values, such that the sum of them is equal to 0. So we are now in a position to develop this quasi-harmonic steady-state equation, which applies to all of these field problems that I had mentioned at the start of this presentation. On the previous slide, we obtained this relationship here for continuity and said that it has to equal 0 for conservation. But in fact, there can be cases where we perhaps in a heat problem generate internal heat, and perhaps in a fluid flow problem we lose liquid. In other words, this expression here is now equal to this internal source Q. So for example, in the heat problem, we may generate heat to additional internal heating, perhaps from a chemical reaction or some other heating source. In the fluid flow problem, maybe we lose liquid due to saturation of the media by the liquid. So this becomes our general expression for continuity. We can now express or obtain a general expression for flow. This could be flow of heat or flow of liquid is equal to minus K times the gradient of the variable in the field function. So for example, if we're considering temperature in a heat analysis, phi here would be temperature, and this would be the change in temperature over a length L. This would be conductivity, and this would be flow of heat. We introduce the minus here because normally we assume that Q is positive as we go from a higher temperature to a lower temperature. This expression could also be used, for example, for fluid flow. In this case, phi would be pressure, change in pressure over a certain length. K would be permeability, and Q would give us the flow of liquid. And similar things apply for the other field functions, where phi could be perhaps voltage or current and so on. We can express this for a three-dimensional material like this. In this particular case, K is a constant for an isotropic material, so it has the same value in all three directions. If we now feed this into here, we end up with this quasi-harmonic equation for these field problems. This is general. I've also introduced Kx, Ky and Kz for an anisotropic or orthotropic case. The equations down here at the bottom are simply an alternative way of expressing this general equation. So just to emphasize again, this is the governing differential equation, second order differential equation for these field problems, which would apply. We use a different field variable here, depending upon whether it's heat or pressure or whatever, and we use different material properties here. From this point on in the presentation, I'm really only going to consider heat transfer and the governing equations for heat transfer and how we convert these to equivalent finite element equations. However, the equations that we derive can be applied to any of the other field problems that I had outlined at the beginning of the presentations. And indeed, actually, one of the tutorials, tutorial number 6, considers flow under a dam where we have pressure and fluid flow, and it uses the features provided in FreeCAD and Calculix for heat analysis to do this fluid flow analysis. So to get it to run, you have to replace conductivity with permeability, you replace temperature with pressures, and exactly the same finite element solution is performed to predict the fluid flow rates, for example, under this dam structure. So it's just to give you an idea that we can really use the heat equations that we develop for other field analysis problems. On this slide, I just want to summarize some of the main equations that we will be needing for this heat transfer problem. On the top left is a 1D view of flow through a material. There is flow on one side of this strip, Qx, flow on the other side with a gradient due to temperature gradient within the 1D strip. We can have heat losses due to convection, or also possibly due to radiation. In the derivations I shall be going through, I will not be considering radiation. There is also a possibility to have flow of heat from the surface as an imposed flow of heat. Convection is also a kind of imposed flow of heat, but it depends upon the surface properties and the difference in temperature between the environment and the surface itself. On the top right here, we have other important equations we will be using. For example, for a given volume, we have to have a balance of energies within the system. So the energy flowing in, the rate of energy flowing in, plus the rate of energy generated within a given volume, have to equal the rate of energy coming out of the system and the rate of energy that will be stored within the system. So that is simply expressed here. We have some other important equations which I've listed here. Heat conduction, we've met this so far several times. The flow per unit area is the conductivity times the temperature gradient. So we have a difference in temperature over a certain distance, delta x. For heat conduction, this is the governing equation. So the flow of heat from the surface depends upon this heat transfer coefficient, which is a property of the material and the type of surface. And it also depends upon the temperature difference between the surface itself and the environment temperature. Heat generated, the rate of heat generated within the material, is this heat source multiplied by the volume. And the energy stored, the rate of energy stored within the material, is the density times this material property called capacitance times the volume times the derivative of temperature with respect to time. I've listed here typical properties, consistent units. So for each of these different quantities here, they would have units depending upon, for example, these kind of material properties or heat properties. From the previous equations, we can derive governing equations for different types of heat transfer problems. And I shall be showing that on this slide and the next slide. If we consider just a very simple 2D element, in this case size dx dy, we have inflows here and here, qx and qy, and outflows here and here. These q values denote energy divided by the area, or divided by the length in this case. And these terms are, of course, the gradients expressing the change of these values over their length dx and dy. Using this energy equation we expressed on the previous slide, we can obtain this expression here. So in this case we have qx multiplied by dy, qy multiplied by dx, and we're going to account for what's happening over a time interval dt. So this becomes the inflow of energy, and this is our expression for outflow of energy. The energy generated is given here. It's the Q due to the possible internal heating source, multiplied by the time interval dt and the volume dx dy. The internal energy that may take place or may be created during this process is given here. It's modified actually from this expression here that we had on the previous slide. So in this particular case we end up with the density multiplied by the capacitance of the material, the temperature change, and the area. The time interval dt in this case cancels out. So this equation is used on the next slide, which after simplifying gives us fairly easy expressions to deal with. For this simplification, we note qx is equal to this and qy is equal to something similar but in the y direction. The differentiation of that leads to this expression here. And as I say, we have similar expressions for qy and the differential of Qy with respect to the y direction. Now if you feed those into that previous expression and you simplify, you end up with these two expressions here. This will be for an orthotropic material with different conductivities in the x and the y direction, and this would be for an isotropic material where we have the same conductivity in both directions. So this would be the general expression for heat transfer in a material, 2D material in this case, but the extension to 3D is obvious, which has a heat source, internal heat source, and also has the potential to store energy due to the capacitance of the material. There are variations of this equation. So for example, the Fourier equation considers transient flow without a heat source. So we have this. The Poisson's equation is for steady state with a heat source. So this becomes our governing equation. Because it's steady state, it means we neglect this effect. And the Laplace equation is a further extension where we neglect internal heating, and we also neglect the mass or capacitance effect here to give us this equation. So these are three variations of these governing equations shown here. And what I will be showing in the next part of this lecture is how these equations, these governing equations, are modified or converted into equivalent finite element equations. So the aim of a heat transfer analysis is to use one of the governing equations I showed on the previous slide. For example, if it's transient with capacitance and time effects to be taken into account, then you have to use the Fourier equation. If it's steady state with a heat source, you have to use the Poisson's equation. And if it's steady state without any heat source, then you apply the Laplace equation. And then either of these equations has to be solved over the complete domain. You also have to impose necessary boundary conditions. So essential boundary conditions will be required at some points to specify temperature. It may also be necessary to add to this non-essential boundary conditions, which could be an imposed flux at some particular points or surfaces of the domain. And a variation of this imposed flux could be convection heat loss, which would involve the equation concerning surface heat coefficient, or surface heat transfer coefficient, and the difference in temperature between the surface and the surrounding environment temperature. So all this would have to be solved. This can be done for very simple problems for the domain, but usually the easiest is to apply finite element techniques. So in the next part of this presentation, I will be showing how you can convert these governing differential equations to approximately equivalent finite element equations and perform analysis as a finite element problem. This part of the presentation moves on to developing the finite element equations that can represent the different types of governing differential equations for the different types of heat transfer problems we considered in the previous part of this presentation. Again, just to remind you, the different types of governing differential equations are usually either the Fourier, the Poisson, or the Laplace representation. And each of these governing differential equations has to satisfy necessary boundary conditions. The finite element equations for this can be derived by either the Rayleigh-Ritz method or the Galerkin method. In this part of the presentation, I'm only going to use the Rayleigh-Ritz method. It's a little easier to explain, and it's also consistent with what I did in the video on chapter 1, where we looked at these methods for 1D elements. For the Rayleigh-Ritz method, we need to develop a functional, which is analogous to what we used in the first video on chapter 1, using potential energy. And this has to be minimized for the system. It also has to be capable of satisfying these non-essential boundary conditions. So to do this, I'm just going to use a 1D problem. I've showed a tapered bar there. It has a prescribed boundary condition at the start, overall length L. We have a prescribed boundary condition, some heat flux at the right-hand end. So this prescribed flux is in fact a non-essential boundary condition. In this case, we only consider convection heat loss around the parameter. So this bar is a rod in shape, a tapered rod. And in the small diagram denoted B, we have a small elemental section where we have heat energy flowing in and heat energy flowing out. We have our usual gradient for a change in the energy flowing out. We have convection heat loss around the complete parameter. And we also consider internal heat generation here. I'm not going to consider in this particular case this mass effect, time-dependent mass effect due to density of the material and capacitance of the material. So this is the same as the Poisson's problem in effect, because we do have internal heat generation being considered. But this, the derivation here would also apply to the Fourier problem if we just neglected this internal heat component. This becomes our balance of energies, heat energies for this particular problem. This is our inflow. Here is our outflow. This is the additional internal energy created due to this heat source Q. And this is the heat loss flux around the parameter due to convection. This is the heat transfer coefficient for the surface, and this is the difference in temperature between the surface temperature and the environment temperature shown here. P is the parameter, A is the sectional area of this. We use our usual flow equals negative of conduction and the temperature gradient, which is plugged into this term here. And after simplifying, you end up with this energy equation here. This equation then has to satisfy essential boundary conditions, which would be the temperature at the left-hand end, imposed temperature, and it also has to satisfy the prescribed flux flow at the right-hand end, which is expressed in a slightly different form. Using this, we can express that equal to this particular relationship here. On the previous slide, we derived an energy balance equation for this elemental section in this rod or bar element. And we also stated the boundary conditions that have to be fulfilled, or possibly fulfilled. At the top here, there is a functional that is suited for this particular problem. Now I'm only stating it here, I haven't given a rigorous derivation of it, but this functional is basically a functional of all the energy terms that has to be minimized. And you see, for example, if you look for the stationary condition by differentiating this with respect to temperature, so we're differentiating this, you will obtain the energy balance equation given on the previous slide. Also, it can satisfy the non-essential boundary condition that we stated on the previous slide because we have this dt dx term in here. So I think for now just accept that this is a valid functional for this particular element. And we can use the Rayleigh-Ritz method in order to convert this into a element equations for this heat transfer. If you consider the normal relations we have for a bar element, a 1D element, the variation of temperature would be the shape functions and the nodal temperatures. This is identical to what we've used before for displacements, where the displacement at any position along the bar is in terms of nodal displacements, but here we're using it in terms of temperature. So the abbreviated form is given here. T1 and T2 would be the temperatures at the two nodes of that elemental section on the previous slide. Differentiating this, we have this expression here. So this in effect is our B matrix for this particular element, relating the change in temperature at any point to nodal temperatures, in abbreviated form given here. If you look closely, this expression is exactly the same as this expression here. You have to consider that the nodal temperatures transpose and the differential here, the B matrix transpose, multiplied by the B matrix and the nodal temperatures is the same as this quantity squared. Similarly, T squared from here would be T transpose N transpose multiplied by N transpose, N and T. Some of the terms can be brought outside of the integral, as I've done here. But this here represents this term. This here represents this term, and these two terms are represented by these expressions, where we've used nodal temperature vector and the shape function matrix for the element. If we differentiate that functional on the previous slide, so we're now doing this in order to find the minimum, and this is a stationary point again, we will obtain this expression here, where K is given by this, KH is given by this, T is our temperatures, nodal temperatures for the element. We have this squared, so it just becomes temperature. And on this side, this will be cancelled out. So we end up with just these. So this term here is our conductivity matrix for this element. This term here is a matrix that's computed for elements that have convection flow at the surface. It's only done for these particular elements. This is a vector created due to this internal heat source, and this is a vector created due to convection flow from the surface. So these two are both related to convection flow from the surface. So this is our system of equations. We would use the same standard assembly methods to obtain the total global system, and we would obtain nodal temperatures by assembling this, inverting it, bringing it over to this side and multiplying by the sum of these two vectors here. As I mentioned, the dn dx is our standard B matrix. So an important point here is all of these elements that we've derived in the video concerning chapter 2 are valid for these types of analyses. This B matrix is simply dependent upon geometry. It is not a function of what type of analysis we're undertaking. K plus KH is the sum of the element conductivity. Obviously, K is computed for all elements in the problem, and as I mentioned, this is only computed for elements that do have convection at the surface. These are our internal or heat generation and surface flux vectors due to convection, and this is our nodal temperature, global nodal temperature vector. This last slide of this part of the presentation tries to summarize all of the finite element equations for heat transfer analysis. These equations would apply in 1D, 2D or 3D. It just depends upon the type of element you would be selecting. If we look at the governing equation up here, the governing set of equations, some of this we've already met, some parts are new. I'll go through each. So far we've met this conductivity matrix for an element. It's given here. It's very much the same as the elements we used in mechanical analysis. The B matrix is exactly the same. It depends upon the element we select. The E matrix now contains material properties of conductivity. So if the element was to lie in the XY frame, we would have a diagonal conductivity matrix with a value here and a value here. If it's isotropic, they will be the same. If it's orthotropic, they will be different. If these principal conductivities lie in some frame that's out of the oblique to the Cartesian frame, then you will have to do a transformation of this to get the values of conductivity in the Cartesian frame, and this is what would have to be used here because these B matrix are formulated in the Cartesian frame. Anyway, this is the element conductivity matrix. The surface convection matrix is computed only at elements which have convection, and this is the form. We've already met this, and the ds here denotes the surface. We've already met this matrix, or this vector, sorry. It contains the heat transfer coefficient for the material, the environment temperature, And this allows us to convert the element values to nodal values. Again, this is only done on element surfaces, or on surfaces of elements that have convection. And we've already met this matrix, or this vector. This is due to internal heat generation Q. And again, this operation here is basically done over the volume for each element. And the shape functions here convert the internal heat generation to nodal values. We have a new vector here, which is actually very similar to this one. It is for imposed surface heat flux. So again, this is only computed at surfaces where you have an imposed surface flux. And these shape functions convert this value to nodal values. What is rather new here is this capacitance matrix. This is due to stored energy. It depends upon the density and the heat capacitance of the material. It is used in this term here, and as you can see, it's a function of temperature change with time. So this analysis, if this is included in the analysis, then it becomes a transient analysis. And I do discuss methods to tackle this sort of problem in chapter 3 of the book. Very often we neglect this, in which case the problem is usually steady state, linear. If, for example, these properties varied with temperature, then it would become a nonlinear problem, and you would have to use a nonlinear implicit method like Newson-Raphson. If the boundary conditions changed with temperature, it would also be nonlinear. You could also imagine cases where you're doing a coupled heat and mechanical analysis, and if the mechanical properties are temperature dependent, that would also be a nonlinear problem. But in most cases, if this capacitance effect is neglected, it is steady state, and we can compute the nodal temperatures directly. I think it's clear we would do a assembly of all of the elements, all these vectors and matrices to obtain the global system, and from this we would get the nodal temperature T distribution for the complete domain. These are regarded as non-essential boundary conditions. If they are in your problem, then you should include them, but we do have to impose essential boundary conditions, which will be some kind of fixed temperature at some points. So I hope that gives a reasonable summary. It is quite perhaps difficult to understand, and I think the last part of this presentation can be useful because I use some of these matrices and vectors in a very simple problem, and you can see how these are applied, and I think it will be helpful in the understanding of each of them. Finally, I just want to go through this 2D heat transfer example I've selected. It's a fairly simple problem, but hopefully it will clarify the application of some of these equations, and then I'll just do a quick wrap up on the chapter itself. This is the problem I've selected. It's a single element, so we're going to apply the finite element equations to this single element. There is a 200-degree input temperature at this side, and we have heat convection from the surface applied at these two surfaces. This is the heat transfer coefficient value for this particular surface. It's a typical value for steel, and the environment temperature is assumed to be 25 degrees C. So obviously the temperature will come in here, it will propagate through the material, and there will be heat loss from these two surfaces. So we end up with some kind of a reduced temperature at this point, which we want to try and find. Dimensions of the plate are given here. And as I say, I'm just going to do this as one single finite element to show how these different equations are computed. An important point here is that you have to, with any finite element analysis, you have to use consistent units. And I will go through this a little later on in the video 7, or lecture 7 as it would be. All analyses have to be in consistent units. So for example, if these are the units we are using here, or the input units specified, and our thickness is in millimeters, and the plate dimensions in millimeters, then this, for example, should also be in millimeters. And the equivalent quantity for this in millimeters would be 40 milliwatts per millimeter degrees C. So it's a simple conversion. And also this heat transfer coefficient will have to be converted to millimeters squared, which is given here. Now there's one point perhaps I should explain a little better. I've used the terms transient and steady state several times during this presentation, and perhaps it's not quite clear what I mean by that to some of you. If we were to suddenly apply this 200 degrees at this particular point to this plate, and this plate had an initial temperature of 25 degrees, then it would take time for the heat to move from this point through to here. Each point within this material would slowly heat up. There would be this internal storage taking place. And this was shown to depend upon the density of the material and the capacitance. This was a term that we had in the governing equations. Eventually, this storage will reach a saturation point, a kind of saturation point, and it won't take in any more energy. And the effect would be that, for example, let me try and draw something here. If we had a graph of this, and we considered some point here, it would take time for the heat to move through, but eventually when the heat reaches this point, it will start to increase this internal storage, and then it will kind of become saturated and become constant. And if we were to look at the temperature of this point, it would be 25 degrees, and then once the heat reaches this point, it's transferred through to this point, it will start to increase, and it too will then reach some kind of a saturation, or a constant value, let's say. Any point closer to the heat source would increase in internal energy earlier, and would probably have a slightly higher temperature, because there will be a loss from this point to this point. Now, modeling all of this phenomena in here would be a transient analysis. It would take time. And you could do that using this Fourier equation, which includes the heat capacitance and density terms, and this matrix I had showed on a previous slide. As I say, you have to analyze that in a transient analysis. You could use an explicit algorithm, for example, but that probably wouldn't be very efficient because this phenomena could take tens of seconds or even minutes depending upon the material properties. And the small time step in an explicit algorithm would make this rather slow. So normally a Newmark method implicit analysis would be used. I have described this briefly in the video to chapter 3 of the book. So that would be lecture 3, but I'm not going through it here. If we were to ignore this capacitance term in the equations for this flow process, then what we would obtain is the steady state results. We would obtain just these temperatures when the whole process has reached this steady state. And that is in fact what we are doing here. We are going to use this equation to represent this particular problem. We have the conduction for the material. This is a necessary convection matrix because of these two surfaces here which are heated. This will be our nodal temperatures, and this will be also a vector related to these convection flows on these two surfaces. So this is the problem we want to analyze. This is non-essential boundary conditions. We will impose the essential boundary conditions in here, which will be 200 degrees C. We will do this later. And this will, the solution of this will provide us as with a steady state result for the final temperature distribution. So first of all, here we compute the element conductivity matrix for this single element. It is given by this expression here, which can be simplified to this expression. We're using in effect the constant strain triangular element that was derived in lecture 2. The B matrix for this constant strain triangular element applied to this single degree of freedom element is given here. If you do look back to the derivation of that element, you will find a lot of zeros in this matrix. You can cut out these zeros because we only have one degree of freedom, and this is in effect the B matrix for this element. And just to remind you, for example, y23 means the coordinate of node 2 in the y direction minus the coordinate of node 3 in the y direction. x13 is similar, for example, the x coordinate of node 1 minus the x coordinate of node 3 for this triangular element. So this is my B matrix. This is the transpose of the B matrix given here. The integral for this simple element can be replaced by the area and the thickness. And the property matrix for this particular heating problem, thermal problem, is this matrix here. We're assuming isotropic properties, so we just simply have a diagonal matrix of the thermal conductivities for this particular material, which were given on the previous slide. So the B matrix is given here. If you were to compute that out, this is the area. These are these difference in coordinates that I've just mentioned. And then you can introduce this B transpose and B matrix into this expression. Gives you this. Here are the thermal conductivities again. And that then is our conductivity matrix for this single element. Normally, of course, you would have several elements. You would compute this for each element, and then you would have to do an assembly of all the different elements. But in this case, we just have this one single element. So the next step is to compute this convection matrix, KH, at the top. This applies only to these two surfaces shown here and here. The matrices are given by these expressions. If you were to look back to the slide where I summarized these expressions, you will see this. However, in this version, I have replaced the surface by the thickness, which is 1 millimeter, and we're going to be integrating over the length. And these n functions, the shape functions, are the shape functions for a 1D line element. If this was convection from a shell element or the face of a solid element, these would be shape functions for a 3 or a 4 node face, depending upon what type of element it would be, triangle or quadrilateral. So here are our shape functions for this 1D line element. This is the transpose, and this is the simple n values, that's here. H, of course, is my surface heat transfer coefficient. And as I mentioned, we're replacing the surface by the thickness and integrating over the length. If you do this multiplication and integration, you will end up with this matrix here, which gives you these values here. I'll leave you to do exactly the same for the edge 2, 3, which has a length of 112 millimeters. And you should obtain this expression here. Now these two can be added together. We do this using a very simple approach by expanding and including the degree of freedom that's not represented. So for example, for the 1, 2 face, 3 is not represented, so we just introduce zeros here. For the 2, 3 face, 1 is not represented, so we had zeros here. And then these two can be added together and can also be added to the conductivity matrix we had on the previous slide, giving us this matrix here. In this particular case, these two added together gives us a full matrix. But normally when you have many more elements and some of the surfaces are do not have a convection flow from the surface, then you will find that it will not be a fully populated matrix and there will be many zero terms present. So the next step is to convert or compute the heat convection vectors, RH, for these two surfaces. These are given again by these, or given by these expressions. Again, it's integrated over the surface, so we can replace that by a thickness and the length integral. It involves the environment temperature and involves the heat transfer coefficient for this particular material. It's very similar to the previous operations, except now we only have n, the shape function, appearing once, and in effect this operation is going to provide us with nodal values here and here for this surface convection, and this would be the values at the nodes for 1 and 2. Similar thing is done for edge 2 and 3, giving us convection quantities at nodes 2 and 3, given here. And these two can also be added together to give us a total heat convection vector for the complete problem. This is fairly straightforward. I think you'll be able to follow this. So finally, we can put things together for a solution. Here is our heat convection vector. Here is our summation of the conduction and additional matrices due to surface convections. This is our system of equations to be solved. In this particular case, an easy way to do this is to impose the temperature T1 equal to 200 and T3 equal to 200. These are imposed essential boundary conditions. We can put those in here and here. These first two equations become, in this particular case, they're meaningless because we've entered these 200s in. But if you multiply this by these terms and rearrange, you will find that T2 is equal to 182.7 degrees C. So we've got a reduction from 200 here to 182.7 degrees at this point. And this reduction is, of course, due to this flow of heat from these two surfaces. This is the steady state temperature. From this analysis, we have no ideas how long it takes to reach this steady state, but this is what would be reached after a sufficiently long time. I have done a finite element analysis of this using FreeCAD and Calculix, and these are the results shown here. In this case, we impose the 200 degrees here, and the analysis predicts 182 degrees at this point. So a fairly close comparison. There are 3 tutorials in the second part of the book using FreeCAD and Calculix, which undertake thermal analyses. Each has a somewhat different aims and objectives. In the first one, tutorial 6, there's a thermoelastic example. First of all, considering the deformations due to thermal loading of a bimetallic strip. So a thermal analysis is performed to get temperature distributions, and these temperatures are then used in each of the 2 materials in this bimetallic strip to compute different stresses and strains due to the different thermal expansion of the material, and then to predict the deformations. There is a second example in this tutorial also that uses the same sort of techniques. It considers the cup, which is shown here, which is suddenly filled with hot water, to predict stresses that are created due to this thermal expansion that takes place, and to estimate the failure of this, which does occur in practice. In tutorial 9, the same cup is analyzed as a transient problem. So in this case, we include this term of the capacitance and density of the material in order to predict how the hot water transfers heat through to the handle. And you can see the sort of either fast heating up, which takes place at nodes very close to the hot water, and the slow heating up, which takes place at points on the handle where it's being held. The last example is this contact problem between 2 metal rings and a rubber seal. This does involve temperature, and it also shows an example where in the contact you can have heat exchange between the different parts. There are a few things within the book that I go into a little bit more detail than I've been able to do here. For example, I do show the Galerkin method to derive heat equations. The equations that are derived are obviously the same as what we've already shown using the Rayleigh-Ritz method, but it is an interesting application of how to use the Galerkin approach. In that derivation, it's for 2D, and I do also include the capacitance term in the derivation. There's a little bit more information given on how you undertake a transient analysis. There is a brief section which shows the derivation of the shape function and B matrices for a 3D triangular element, which only has 1 degree of freedom at each node. But I think if you did go through that last example and you look at the B matrix and compare it with what we derived for the N and the B matrices in lecture 2, I think you will be able to see the connection there. There's a few more examples given, worked examples on 1D and 2D problems, and there's a short discussion on other types of field analysis. But I think essentially I've covered most things that I wanted to in this presentation on heat transfer, and I hope it's given you some idea of how these analyses are undertaken. In the next video, covering chapter 6 of the book, I go into constitutive models. In the tutorials, different materials are used, and I thought it would be useful to explain elasticity, isotropic and orthotropic, also hyperelasticity and plasticity in a little bit more detail, and that's the aims of the next video.